Hello everyone, I'm Vidya, part of Rail Civils team at Arcadis UK. I'm joined by my colleagues Rajesh Raman and JNPK, who are based in our Global Engineering Center in India. We're going to take you through High-Speed 2 Birmingham Curzon Street station detailed design phase with focusing on Viaducts packages. This is a brief outline of our presentation today. I will give a project overview. Rajesh will then take you through modeling strategy. He will also give details of global analysis and local FE models that we developed as part of the design. Jayant will then take you through rail structure interaction analysis, which formed a key part of Viaducts design. This is a route map of High-Speed 2 project in its current form. There are 4 stations starting from London Euston and ending with the Birmingham Curzon Street station, which is terminal station building. The route length this phase is about 140 miles. And there are 2 depots and 32 miles of tunnel work. This is architects' expectation of High-Speed 2, this Birmingham Curzon Street station. You can see Birmingham city skyline in the backdrop. What is striking here is old Curzon Street station building. Maintaining sightlines to this heritage station building formed a key part of planning consent. There are 7 lines running from east to west, supported by 4 viaducts. The overall length of this station extent is about 460 meters long. Half of the length on the western side is covered. The western concourse is located here above the viaducts, and eastern concourse is located below the viaducts. The station is served by Midland Metro Alliance tram line. And you have taxi rank and other services located on the eastern side below the viaducts. This is site map, and this is old Curzon Street station building, and maintaining sightlines to this station building from this new Canal Street was a key planning requirement. You have MMA tram line running north-south, and you have western concourse here and eastern concourse here. The whole detailed design work package is divided into several sub-packages, and you can see different elements of the station building. At a lower level, you have control room and key functions essential for running of the station, and it also supports all key building services. On the eastern side, you have eastern concourse and some back-of-the-house plant, and you have taxi rank at the eastern end. The next level is viaduct deck level, which supports platforms. A viaduct also supports a number of vertical transportation elements, stairs, escalators, lift shafts. You have platform canopies on the eastern side. The western concourse is supported by viaducts. There are some retail units on the western side, and the western part of the station building is covered by a primer grid roof structure. This is a structural BIM model. This is a detailed view of station looking towards west. You have these viaducts formed by precast pre-tensioned U-beams supported by portal piers. Then you have these platforms which are monolithic with a viaduct deck slab, and then you have concourse beams directly resting on diaphragm beams of portal piers. And you have this roof structure which is supported by steel buttress columns supported at the ground level. This is section through the building. You can see the viaduct deck cross section here, and these concourse columns, which are located about 5 meters away from the track center, mainly from derailment impact considerations. The platform walls are designed for derailment impact. And you can see lift shaft here, supported by these L beams, which run from diaphragm to diaphragm. This is bird's eye view of all the viaducts. You have 3 northern viaducts supporting 2 tracks each, and then southern viaduct supporting 1 track. And you have about 60-meter length supported by piled rafts. And you have a transition span at the eastern end, which it divides the Curzon Street station building, station viaducts from the approach viaducts. This gives spatial extent of individual viaducts. Western viaducts and eastern viaducts are roughly about 200 meters long. And then you have here the tram line and New Canal Street. The key requirement was to eliminate bearings inside the station building. So the only place where we could locate the bearings is the junction between eastern and western viaducts here. This is outside the building, next to the tram line, and towards the eastern end of the viaducts, and of course under the transition span. This is longitudinal section. You can see a number of movement joints, particularly on the western side. The movement joints are typically formed by twin columns supported on a shared pile cap. And the only place where we could locate the bearings is this at this grid line, which is junction between the eastern and western viaducts. There's only one movement joint on the eastern side that is within the station building. Again, this movement joint is similar to that on the western side, which is deck is integral with the piers on both sides, but the deck itself is separated here. And this is the transition span, which is fixed towards the eastern end and with free bearings this side. The movement joint within the viaduct extends through the concourse, but there is no movement joint in the roof. So this is again a key feature of design. This shows the typical construction of viaducts, the precast pre-tension beams. They are brought to site, supported on temporary trestles before they are made integral with diaphragms. And then this span by span construction continues from west to east. This is governed by site constraints. Because As I explained, we need to maintain sight lines to the old Curzon Street station building. So though the columns are located parallel to this new Kellogg Street, this formed a colonnade and frontage for the eastern concourse. And because of the requirement of tram line, the viaduct, the piers supporting viaduct, they are located at a certain distance from the tram line, and it required and the overall arrangement resulted in some skew spans. This shows a bit in detail. And because the maximum length of the beams that can be transported to site is about 28 meters, so we had to come up with some intermediate piers and intermediate diaphragms to break the span. And because of the arrangement of the piers along the New Canal Street, it also resulted in some skew spans. All the substructure and superstructure here is integral, except here where it's located on bearings at the eastern end. Sorry, at the western end of the eastern viaducts. This is a cross section of the deck. There is a waterproofing in the deck, and there is a waterproofing protection, like concrete protection layer, and then there's a slab track, intermediate layer that directly rests on the concrete protection layer, and you have track slab supporting the rails. This is design criteria. The design speed is 100 kilometers per hour, so it's not quite a high-speed viaduct designed for high-speed trains. So the design criteria is similar to that of any other network rail bridge because the speed is less than 200 kilometers per hour. Designed for standard LM71 and SW0. The dynamic loading and natural frequency limits to EC12, except for derailment impact loading governed by HS2 standards. All tracks or continuously welded rail tracks, CWR tracks, no rail expansion joint within the station limits, and this governed all the rail structure interaction and careful consideration of rail stresses. And it's integral construction, no bearings inside the station building. That required, again, challenges associated with the temperature loading, creep, shrinkage, and all those effects. Again, the western part of the station, because of the expect potential rise of groundwater level, it's designed as grade 3 basement. So the basement slab is integrated with the pile caps of viaducts. And again, that was again another design challenge. As I explained, deck is formed by pre-tension U-beams. The maximum length is about 28 meters. Because viaduct supports a number of vertical transportation elements, escalators, stairs, lift shafts, controlling of viaduct movements, again, was a key part of the design. And again, the span-by-span construction from west to east governed by site logistics. Again, they put some additional loading, and we had to do a careful construction stage analysis. Because of the integral construction, temperature loading governed the design, and to mitigate that temperature load effects, we proposed concrete mix with limestone aggregate. It allows to use a reduced quotient of thermal expansion compared to normal aggregate. And because of the size of the concrete elements and the seasonal nature of the temperature effects, we proposed to use again a long-term modulus equal to 75% of the short-term modulus. This is suggested in a book by Robert Benham. You can see the reference here. We built this into AIP and we got approval from HS2. And again, because the whole viaduct structure comprises reinforced concrete elements and pre-stressed elements, so using reduced stiffness, cracked stiffness for RC elements, mainly the piers and diaphragms, also help to come up with a realistic temperature loading. And also for long-term load cases like differential settlement and long-term shrinkage, we used long-term Young's modulus considering the creep. In terms of using this cracked stiffness, the current edition of EC2 allows to use them for ULS, but for SLS cases, we had to consider gradual evolution of cracking. So we put a limit on the cracked stiffness in the analysis. Whereas second generation of EC2 makes it very clear for any deformation-induced loading, you can consider crack stiffness even at SLS. I'll now give it to Rajesh to take you through the modeling strategy and global analysis. You can request control, Rajesh.
Requested.
Yeah, okay.
You can see, right?
Yeah.
Thanks, Vidya, for this. I'll be taking you through this modeling strategy and the workflow of global analysis. So this, as explained earlier, the structure is bifurcated into eastern and western. This is the western viaduct, which has a total length of around 195 meters separated by movement joints at 3 locations. The maximum integral span is around 65 meter here, as this entire viaduct stretches within the station building. No bearings are provided. The piers are either square or rectangular in shape. This is the model showing eastern viaduct. Here there are some span with skewed diaphragm and pier due to existence of canal street, highway and tram line passing below. The total length is around 200 meter with maximum integral length of 90 meter. In this viaduct, the bearings are proposed in location outside the station premises. Also, the pier shapes are governed by aesthetics to accommodate drainage and downpipes. Uh, this all the viaduct configuration it was been modeled in using MIDAS civil with combination of grillage and finite element techniques to capture the structural behavior accurately. So this is the grillage model snips. So this was consisting of like pile caps, piers, diaphragm. These were all were used modeled using beam elements. The deck system it simulated as a composite element integrating precast U beams with cast in situ deck slab to reflect the composite action. The plate element usage was also done like it was incorporated solely to facilitate accurate load distribution to longitudinal beams without contributing to global stiffness. The material properties were concrete time-dependent behavior to account for creep, shrinkage, and age-dependent modulus. Then boundary conditions were pile 6 by 6 stiffness matrix. The bearing at integral locations, it was all were modeled with rigid links, and at bearing locations, it was like elastic links. The beam deck interface, this is where we had provided elastic links to simulate interaction to accommodate differential behavior, which I'll show on this slide. Yeah. So this here the composite action and load distribution slightly briefly tell you. As observed, the longitudinal beams are closely spaced, forming a robust relay system to support the deck. At pre-composite stage, prior to casting the deck, the structure system comprises of isolated U-beams. Load transfer is primarily through individual action with limited transverse interaction. Uh, Post deck, after the deck is cast, elastic links are introduced between the beam nodes from longitudinal grillage and deck nodes. Uh, these links act as stiff transverse outriggers. You can see these are the stiff transverse outriggers, enabling effective load sharing across adjacent beams. So this modeling approach ensures uniform distribution of transverse loads across the longitudinal beams, enhancing uh, structural efficiency and serviceability. This methodology is consistent with principles outlined in E.C. Hamley's bridge deck behavior. Uh, this is an isometric view of one of four span viaduct uh, analyzed. So here you can see to simulate realistic structural behavior under service and ultimate conditions, cracked stiffness properties were incorporated into the model. Piers and diaphragms were assigned crack stiffness throughout the analysis to reflect reduced flexural rigidity due to cracking under sustained loading. For deck slab, crack stiffness was applied only under ultimate limit state conditions, aligning with design code provisions and ensuring conservative assessment of load effects. The pile group beneath each pile was modeled using 6 by 6 stiffness matrix within the general spring supports framework in MIDAS Civil. So the stiffness matrix accounted with for 3 translational and 3 rotational degrees of freedom. And we carried out a sensitivity analysis to account for uncertainties in soil stiffness and pile soil interaction with the lower bound stiffness of -30% and upper bound stiffness of +30%. These bounds were analyzed using actual spring elements in MIDAS to evaluate the impact of global structural response and foundation performance. Uh, this is the complete geometry of the grillage model, and below is the rendered image. Let me take you to the construction stage analysis. So these are the snips from BIM model for the construction staging. The pile caps cast first, which is eminent, and then the piers. The beams are placed on temporary supports. These supports are placed on pile caps or hard standings as seen in the previous slides. The first stage of casting will be the diaphragm, and see here the and part of the deck, say up to 1/5 of the span. The next stage would be the remainder of the deck of that span, along with the diaphragm and part of the deck of the next span, and so on. You can see this like we can see this. These are the snips from one of the analysis models wherein construction sequence tools are used from MIDAS software. Can be seen that the sequence in the BIM model is aligned with the design. Here it can be seen the pin supports, which are temporary supports. These are activated for the beams and then deactivated as the diaphragms and deck achieves its desired strength. This is the viaduct structures were analyzed for seismic loading in accordance with the relevant UK design standard. So these are seismic hazard mapping. Uh, a response spectrum analysis was conducted using MIDAS Civil again to evaluate the structure's dynamic response under seismic excitation. Site-specific response spectra were generated based on peak ground acceleration values, and soil classification, ensuring accurate representation of seismic demand. This approach allows for assessment of modal contributions, base shear, and displacement profile under seismic conditions, ensuring compliance with performance criteria for critical infrastructure. This to address the transverse behavior and ensure accurate simulation of deck performance, full 3D finite element model was developed using plate elements. The model provides a detailed representation of the deck geometry, including slab thickness, the diaphragm, and beam spacing. Plate elements were used to capture bending, membrane, and shear effects in both longitudinal and transverse directions. Accidental loads were considered. Train derailment loads applied transversely to simulate impact loading and eccentric loading conditions. These scenarios were analyzed to verify structural robustness and compliance with safety requirements and extreme events. Uh, this modeling approach ensures that both serviceability and ultimate limit state criteria are met, while also validating the deck's resilience against accidental transverse loads. Uh, this is this is the interface span connecting the mainline viaduct and the station of the station viaduct uh, to the approach span viaduct. This is constructed in as cast in situ simply support. This is a cast in multi simply supported cast in situ multicellular reinforced concrete RC deck. Like unlike station viaduct span, which utilize precast pre-stressed composite decks, this interface span adopts a monolithic RC construction to accommodate geometric and structural continuity. And the span geometry and structural detailing are aligned with the BBV approach viaducts, ensuring seamless integration in terms of profile and load path continuity. This slide presents a simplified view of grillage model used for structural analysis. The load longitudinal grillage members were positioned such that the centroid of each member aligns with the centroid of overall deck cross section. This alignment ensures the representation of bending stiffness and load path continuity in longitudinal direction. Uh, Transverse member properties were based on the principles outlined in EC Hamlet's bridge deck behavior. This slide illustrates the stick model adopted for structural analysis, representing the viaduct in a simplified yet structurally meaningful form. The stick model serves as a computationally efficient tool for evaluating global structural behavior while maintaining alignment with detailed FEM outputs. Yeah, this slide presents a snapshot of a 3D finite element plate model developed for transition span deck. The 3D FEM model was created to perform a detailed stress analysis across various deck components, including slab panels, diaphragms, beam flanges, and webs. Uh, the objective, you can say, is to evaluate stress concentration under service and ultimate limit state, and validate structural performance under complex loading scenarios, including live load, temperature, and of course the accidental derailment effects. Uh, there were some additional checks to ensure structural adequacy were carried out on the outer web of the deck. These were carried out in accordance with the BSEN 1992 of Eurocode, which is design of concrete structure for bridges, specifically Annex MM. These results were extracted from 3D FEM plate model. This check reinforces the robustness of the design, particularly in regions vulnerable to lateral and eccentric loading. Uh, this is the 3D image of FEM model showing the displacement, which was very essential for, as this was a multidisciplinary project, and it displacements, this SLS displacements were very crucial for other services. That's it for the modeling. Uh, I'll now hand over to Jayant, who will be taking forward for with rail structure interactions.
The aspects related to rail structure interaction analysis for Curzon Street Station Viaduct. A brief introduction on rail structure interaction analysis, why we need to perform them before we go into the analysis performed for Curzon Street Station Viaduct. In rail structure interaction analysis, we check the additional stresses that are generated in the rail, the decant displacements, and the additional forces the substructure is being subjected to due to this interaction. These additional forces or stresses that is generated in the rail happen because the rail is continuous over the bridge deck moment joints. So essentially, when the bridge deck moves due to variable actions such as temperature or vertical load, it tries to pull the rail along with it. And this is resisted by the continuity of the rail and the rail being held by fasteners in a ballastless track system or by the ballast in a ballasted track system. So due to this, the resistance happens until the rail slips once it exceeds the fastener or the ballast capacity. So until that, the force will be generated in each fastener. So this, builds up, this force builds up, and that's how the force gets generated in the rail. So if the tracks are uh, discontinuous, let's say you're cutting off the track exactly at the bridge moment joints, both of these ends, then essentially the track will move along with the bridge. So there'll be no relative displacement bridge between the bridge and the tracks. Then there'll be no additional forces generated in the rail or in the bridge substructure. So this the interaction phenomena essentially happens when the rails are continuous over the bridge deck moment joints. Yeah, that's a short brief on the background to the rail structure interaction analysis. For rail structure interaction analysis, we refer to a number of documents. Essentially, the UIC standards and the Eurocode standards are helpful in this. In UIC, we refer to 7743R that forms the background to the Eurocode standard that covers the ballasted system. And for a ballastless track system, we have the UIC recommendation for design and calculation of ballastless track note. And in Eurocode, we refer to BSEN 1991-2 and and also the new published document 17231. I would like to emphasize here on the new published document 17231 as it covers in detail the background and the concepts of rail structure interaction analysis. And also the published document has the revised provisions to be incorporated in the next update of 1991 Part 2. We saw earlier a brief on Rajesh covered the brief on the deck moment joint. So here I'll be talking specifically on the rails. So the rails are continuous for the full extent of Curzon Street Station Viaduct. That's from grid line 2, about 10 meters from grid line 2 till the end. That's in near grid line 17. That's this transition span. So the overall length of the rail is about 481 meters. The scope of rail structure interaction analysis for Curzon Street Station Viaduct was to get the additional stresses in the rail within this extent of 481.34 meters. And the buffer stop is at a distance of about 20 meters from the track terminal point. And also the rails are not just continuous over the bridge deck expansion joint within the Curzon Street Viaduct, it's also continuous into the approach viaduct. That's the N1 viaduct. Yeah, here we can see the arrangement of the approach viaduct. Here the rails are into the approach viaduct are continuous for a length of about 911 meters. So from this transition in zone, it's continuous for a length of 911 meters, and then we have the rail expansion device here located here. And coming to the articulation of the approach viaducts are all, I'll be covering only this extent of 911 meters. So over this length, it's all continuous with, except at near grid line 3 and 4, that's about 40 to 50 meters from the transition pier location. So for this full extent, it is longitudinally fixed at the grid line 3 and 4. Now, if you look at it as an overall, including the Curzon Street Viaduct, the rails are continuous, starting from the track terminal point to the, till it goes to the approach viaduct for a length of 911 meters. So if you combine both, you can say the rails are continuous for a length of about 1,392 meters. Yeah, this again, it covers the articulation of the approach viaduct, which I spoke in the last slide. Now, for Curzon Street Station Viaduct, because the rails are not on embankment, but it's on approach viaduct, we have to model the approach viaduct because it impacts the the rail structure interaction analysis for the Curzon Street Viaduct also. Now we have to take a decision to what extent should we model the approach viaduct. Should we model the entire 911 meters, or is only a certain extent is sufficient? So we went first with a sensitivity study by modeling two approach lengths of 100 meters and 250 meters. So from this sensitivity study, what we noticed was the stresses in the rail for the Curzon Street Viaduct or the changes were very negligible between the both 100 and 250 meters length of the approach viaduct considered in the analysis. The reason being, what we saw is because the approach viaduct is longitudinally fixed between grid line 3 and 4 in both this 100 and 250 meters length of the analysis. We considered this longitudinal fixity. So the displacements of the deck near the Curzon Street Viaduct was accurately considered in both of these models. So there was not much change in the stresses in the rail for the Curzon Street Viaduct, and both of these were considered. And finally, we went with, since there was not much difference, we went with the approach length of 100 meters. And when we considered for the sensitivity analysis, when we model, we considered for the approach viaduct all the stiffness, that's a ground stiffness, the substructure stiffness, and also the superstructure stiffness of the approach viaduct. And just coming into some of the assumptions we had for the rail structure interaction analysis for Curzon Street Viaduct. Modeling of the approach viaduct, as I covered in the last slide, we took it to be 100 meters based on the sensitivity study. Now, for the track termination at grid line 2, here the track is free to expand and contract. So the track termination point was considered to be similar to a rail expansion joint where it can freely expand or contract. For the buffer stop, which is located near the track terminal point, the fasteners would be closely spaced near the buffer stop. So for both loaded or unloaded condition, the longitudinal stiffness, that is the fastener stiffness, was taken to be 60 kilonewton per meter because the fasteners are closely spaced. And this analysis being done within a station environment, braking and traction can occur in either of the tracks. So we considered a scenario where braking can occur in both the tracks, or traction in both the tracks, or braking or traction in one of the tracks, and took the worst cases for our analysis and checks. Creep and shrinkage, the residual creep and shrinkage effects were considered. That's the creep and shrinkage occurring in the deck after the rails are installed are considered in the analysis. The rail break analysis also was required to be performed here, because we had gone through a departure route, which I'll cover later down in the slides. For the analytical model geometry, a grillage for the substructure stick model was considered. That's a line beam element, and for the superstructure also line beam element. But a grillage model was generated. That's for both viaducts and the pile draft. Then between grid line 2 to 4, it's pile draft. So for that also a grillage model was considered. And for the transition span and the approach viaduct, it's a voided deck, so line beam was considered for the analysis. And for the analysis, the entire the substructure, the ground stiffness was considered, and the pile cap was modeled, and including the tracks was modeled. The track, each track has 2 rails, so it was combined and modeled as a single line with the property accordingly modified. Here you can see a cross-sectional view of the model. So where you can see the ground stiffness considered through a 6x6 matrix, and then the pile cap, and then we have the pier, and where the deck and the substructures integral, rigid link was considered, and where they are through bearings, we had elastic links, completely free where it's free to move, or fully restrained where it's restrained. And then the depth of the deck was considered in the analysis, and then the eccentricity of the rail from the top of the deck also was considered. This is necessary to accurately get the stresses in the rail when due to deck and rotation. And between the rail and the deck, a bilinear spring was considered to model the longitudinal fastener resistance. This is the property of the bilinear spring. Up to a certain displacement, it varies linearly, and then it slips, and the force remains constant in the spring. And here we have the loaded stiffness. It's 60 kilonewton per meter, and the unloaded is 30 kilonewton per meter. This is taken as per the HS2 standard requirement. This is a view of the North Viaduct 2-track viaduct model. So you can see the full extent model from grid line 2 to grid line 17. That's the Curzon Street Viaduct, and then the transition spans here. Sorry, not the transition span, the approach viaduct spans. This is the transition span. This is a cross-sectional view. And this is a single track viaduct, South Viaduct. Here again, the full entire Curzon Street Viaduct, including the pile draft, was model with the approach viaducts. The rail break analysis model is similar to the rail structure interaction analysis model. It's essentially the same model. The only difference being we intently introduce a gap in the rail where we expect the maximum tensile stresses to occur, because at this location we will have the maximum gap being generated. And for the rail break analysis, it's an accidental scenario, so we consider only the temperature action on both the rail and the bridge system. We don't take any live load into account. This is as per the Eurocode requirement. The design criteria, we check the decan displacements and the stresses in the rail. Now on to the decan displacement. The first check is the longitudinal displacement due to braking and traction that occurs at the bridge decans. The limit is 5 mm when the rail is continuous. And then the longitudinal displacement at the decan due to the vertical live loads. This is generated due to the rotation of the deck. And here the limit is 8 mm as per Eurocode standard. And then the vertical displacement of the deck due to variable action again. This is the limit is 3 mm when the speed is less than 160 kilometers per hour, which is again as per Eurocode. Now these deck-end displacements are checked. What is given in the Eurocode 1991 Part 2 is for ballasted track system, but the PD states to use the same limit for the PD 17231 states to use the same limit for the ballastless track system. So for Curzon Street station, the rails are on a slab track system, which is a ballastless track system. The same limits were followed. And for the ballastless track system, there are some additional requirements to be checked. That's the deck end rotations, both at the ends and at the intermediate locations, and also the lateral deformation of the deck at the deck ends. That's where the bridge deck expansion joints are located. So there are limits given in the HS2 standards for this, and these were also checked in addition to the bridge deck ends limits given in Eurocode 1991 Part 2. And for the rail break, the maximum gap limit is 90 mm, and this was recommended by HS2. Coming to the axial stress in the rail, the axial stress in the rail for the ballastless track system is 92 MPa as per the UIC standard. Now, for Curzon Street station, we had gone through a departure route which was accepted by HS2 with a limit of 112 MPa. This limit could be followed when we do a complete analysis by considering the eccentricity of the rail with respect to the CG of the deck. So when we do this, when you consider this in the analytical model, we will be accurately interpreting the stresses in the rail due to deck end rotations. So when the deck is rotating, there'll be some horizontal movement generated, at the deck top level and at the rail level due to this eccentricity, and that movement will lead to an additional stress in the rail. So when we account these eccentricities in the analytical model, we can, we will be accurately, calculating the actual stresses in the rail due to the deck and rotations that's coming from the temperature gradient or the vertical live load. So the limit of 112 MPa can be followed. So since in Curzon Street station viaduct, as we saw earlier, we accounted for these, we use the limit of 112 MPa. Now, coming to the background of this limit is just the additional stresses in the rail when the rail passes over a bridge. This is not, the overall allowable stress in the rail. Now, from a bridge engineer's perspective, if you look at it, the additional stresses in the rail comprises of the stresses generated due to the bridge deck temperature and this stresses generated from braking and traction of the live load component, that's the longitudinal action of the live load component, and the effect from deck end rotation, that's the temperature gradient or the vertical live load action. Now, overall, if you look at it, it's the stresses in the rail will not be just from these action. It will also be due to the temperature in the rail, the residual stresses in the rail, generated during the manufacturing process, and also the bending stresses in the rail. That is both the torsional stresses and also the lateral and the vertical bending stresses. So now, all these combined together with the additional stresses in the rail, there will be there's allowable stress in the rail due to fatigue or track buckling. But from the track system engineer's perspective, they'll be calculating only this component of stress. So once we have the total allowable stress in the rail minus this component of stress generated in the rail when the rails are away from the bridge, we have a balance left out, which is the additional stresses available allowed when the rails are passing over the bridge. Onto the loadings for which the RSA analysis is performed. We have the loading from bridge deck. That's plus or minus 35 degrees as per USC standard, and the loadings from the loadings on the rails, that's a thermal expansion and contraction plus or minus 50 degrees. One thing to note is this thermal loading on the rail needs to be considered only when the bridge is near to the rail expansion joint here, as because then only the interaction effects take place. Otherwise, there will be no interaction generated when the bridge is sufficiently away from the bridge expansion joint, since there will be no relative deformation between the bridge deck and the rail. So here, as the uh, bridge is near the track terminal point, it's about, I think, about 50 to 60 meters, there will be some interaction effects. So this was considered in the analysis. So one thing to note here is when we take account of the bridge, or sorry, the rail temperature action, the stresses in the rail is not 112 MPa or not 92 MPa. It will be 112 or 92 MPa plus the stress in the rail generated due to the temperature change in the rail. That's because these additional stresses doesn't account for these the temperature in the rail. So the temperature in the rail is already accounted in the uh, rail system engineer's design. So since we are now again adding this into our analysis, we can enhance or increase the limit by that extent. That's a stress in the rail generated due to temperature change of rail. And then the other loadings, the temperature gradient and the residual creep and shrinkage actions, and the braking interaction and the vertical live load. And as I covered earlier, for rail brake analysis, it's just the temperature action in the rail in the deck. And this complete analysis was performed for this in MIDAS Civil. This results, as you can see, the maximum stresses in the rail were within the limit of 112 MPa, and as expected, the maximum stresses in the rail occur where the expansion length of the deck is maximum. So that here it is, at the expansion between the movement joint, the location between the Curzon Street station viaduct and the transition span. So we had the maximum expansion length of the deck, and accordingly we had the maximum stresses in the rail, both the tensile and the compressive stress. And you can see, and apart from all the deck and displacements were within the limits specified by Eurocode and HS2 standards. And once from this analysis, we get the substructure forces or the additional forces generated due to this analysis, and this is passed on to the substructure team for checking the substructure, which will be added into the thermal load combination. Yeah, thank you. Now we'll be handing over to Vidya to cover the aspects related to the conclusion.
Thank you, Rajesh and Jayant, for an excellent overview of detailed analysis and rail structure interaction analysis, which formed a key part of viaduct design. I think, as you have seen, because of number of span configurations, we ended up with about 17 different types of viaduct forms. So, along with grillage analysis, we performed a number of detailed 3D FE models. And we modeled pre-stress accurately because accurate prediction of viaduct displacements was critical for supporting the vertical transportation elements and building services. And all the stress checks in the pre-stressing beam were carried out within MIDAS, which was quite helpful. We wish we had done more automation in completing ULS design of all pre-stress beams and all of that within MIDAS. But I think there were some issues in terms of getting the right load combination and coexistent load effects. And for that reason, we ended up doing this ULS design of the beams outside of the MIDAS. Again, the submodeling of large analytical model would have been helpful, but because the viaducts, although the deck is separated, it's not complete. The viaducts are not completely separated between the east and the west because they use a shared pile cap. So the about 200 meters length of the viaduct really had to be modeled in full. And because different teams were working on different viaducts, we could only separate the eastern and western parts. And again, because there are a number of pile caps and we use 3D strut and die model, if this design feature was available in MIDAS, that could have been quite helpful. I think this is a suggestion for MIDAS to think about in coming up with a strut and die model add-in. That's all really. I'll take any questions you have. Thank you.